All right, let's talk about the code that runs, well, pretty much everything. Your plane's autopilot, life support in the hospital, you kind of want that stuff to be perfect, right? But how can you prove it's perfect? That's what we're digging into today. There's this incredible language called linear temporal logic, and it's all about giving our most important systems instructions about time itself. So let's just start with the big one, the question that really matters. Every single day, you and I, we trust our lives to code. I mean, think about it. The planes we fly in, the medical gear that keeps people alive. How can we be absolutely certain that code is going to do the right thing, not just now, but in every single possible future? And that question leads us right into our first section, what I'm calling the certainty problem. Because, there's a huge difference between, hey, it seems to be working, and we can mathematically prove this will never, ever fail. Yeah, this isn't some abstract theoretical stuff. We are talking about the real world. Air traffic control, juggling hundreds of planes at once. Autopilot systems, flying a jumbo jet through a thunderstorm. It even goes down to the tiny logic gates inside the CPU that's running your computer right now. In these systems, a single bug, just one unexpected moment, can be absolutely catastrophic. So you might be thinking, well, can't we just test it a bunch? And we do. We can run millions, even billions of tests. And that's great for finding the bugs you expect. But what about that one in a trillion sequence of events that nobody ever thought to test for? See, here's the key. Testing can show you that bugs are there, but it can never prove that they're not. For that, you need something completely different. Okay, so what is that different approach? Well, that brings us to section 2, a language for time. This is where we get into the solution, which is, well, it's a whole new language designed to talk about how things happen over time. And here's the star of our show, linear temporal logic, or LTL for short. So what is it? Just think of it like a grammar for describing behavior over time. It's perfect for what we call reactive systems. Things that are always on, always reacting to what's happening around them, like a web server or, an autopilot. With LTL, we can write down super precise rules about every single possible future, every timeline that system could ever follow. And believe it or not, this isn't some brand new cutting-edge idea. This goes all the way back to 1977. A computer scientist named Amir Pnueli published this foundational paper, The Temporal Logic of Programs. He was the one who basically said, hey, we need a better, more formal way to talk about what software does over its entire lifetime. And that insight? It kicked off this entire field we're talking about today. Okay, so this is where it gets really cool. How do you go from a plain English sentence to this logical code? Let's look at these two examples. First one, after a request, a resource will eventually be granted. In LTL, that becomes request arrow F grant. The arrow is just if-then. So, if there's a request, then F for finally or eventually, there must be a grant. Simple, right? Now the second one, for a traffic light, a red light will never be followed immediately by a green light. That looks a little more complex. G, red light, arrow not X, green light. Let's break it down. G means globally or always. So always if there's a red light, then the exclamation mark means not, and X means the very next moment. So not a green light in the very next moment. See how that works? We've just taken a vague English rule and made it a precise mathematical statement. There's no room for misunderstanding. So we've got this awesome language, LTL, for writing the rules. But how do we actually use it to check a real system? That's the job of what we call the model checking engine, which is our third section. So how does this model checking thing actually work? It's basically a 3-step dance. First, the engineers have to create a formal model of their system. You can think of this like creating a giant map of every single possible state the system could ever be in, every single choice, every single path. Step 2. They write down the rules of the road using LTL. The critical safety stuff, like the landing gear must always be down before touchdown. Then, for step 3, you unleash the machine. An automated tool takes that giant map and the LTL rulebook and just goes to work, exploring every single path to see if any of them break the rules. And these tools, they're like the most dedicated inspectors you can imagine. They never get tired, they never miss a thing. They're not just looking for obvious problems, they're searching for any possible problem. And here's the best part. If they find a way to break a rule, they don't just give you an error message. They spit out something called a counterexample. And a counterexample is gold. It's a precise step-by-step recipe that says, do this, then this, then this, and boom, the system breaks. It's incredibly valuable for fixing things. But what if it searches everything and finds nothing? Well, then you've done it. You've mathematically proven that for that specific rule, your system is safe. Now, I know this might all sound a bit academic and out there, but trust me, as we're about to see in Section 4, LTL is absolutely everywhere in the real world. Let's start with aerospace and robotics, where the stakes couldn't be higher. We're talking about planning out complex missions for drones, making sure autonomous robots don't crash into each other in a warehouse, and even designing the systems that keep airplanes a safe distance apart in the sky. All of that relies on this kind of formal logic. And it's just as crucial when you look at software and cybersecurity. You know how sometimes a program just freezes? LTL is used to prove that complex software won't get stuck in those deadlock situations. It can verify that your private data isn't going to leak out somewhere it shouldn't. And this is a big one. It's being used more and more to check the basic logic of AI systems. And we can go even deeper. The verification goes right down to the silicon itself. Before a complex computer chip even gets manufactured, LTL is used to verify that the design is correct. It's also used for tricky hybrid systems, things that make software with moving mechanical parts, and for coordinating huge swarms of devices, what we call multi-agent systems. So, okay, we've seen how LTL works in a ton of places where it's already being used. For our last section, let's look ahead and talk about why this is about to become even more important. Really, it all boils down to one simple fact. Our technology is getting more complex and more autonomous every single day. And the more complex it gets, the less we can just hope for the best with traditional testing. We're literally building machines that will make decisions we can't possibly predict. In a world like that, having the mathematical certainty that LTL provides, well, it stops being a nice to have and starts being an absolute necessity. And that brings me to the final question I want to leave you with. As we race forward building more and more powerful AI that's going to control our cars, our power grids, our entire infrastructure, can we really afford to just cross our fingers and hope it all works out? Or do we need to demand a language, a proof, that its logic is sound?